We now learn about differentiation and integration with Maclaurin series. And we'll start with differentiation. As you can see here, I've already written the Maclaurin series for sine of x. And as we know, the derivative of sine of x, so that's the derivative of sine of x with respect to x, is equal to cosine of x. Indeed, this is likely to be one of the first derivatives you learnt. And what's quite convenient about Maclaurin series is that they can be differentiated to obtain the Maclaurin series of a function's derivative. So, given that the derivative of sine of x equals to cosine of x, we can obtain the Maclaurin series for cosine of x by differentiating, with respect to x, the Maclaurin series we see here. In other words, by differentiating x minus x cubed over factorial 3 plus x to the power of 5 over factorial 5, and so on and so forth. So let's go ahead. Differentiating all of this, we quickly obtain 1 minus 3 times x to the power of 2 over factorial 3 plus 5 times x to the power of 4 over factorial 5. And of course, it would carry on forever that way. Now we have 3 over factorial 3, for which the 3's cancel out, leaving us with a factorial 2. And for this term right here, we have 5 over factorial 5, for which the 5's cancel out, leaving us with factorial 4. And so after simplification, we quickly find that the Maclaurin series for cosine of x is equal to 1 minus x squared over factorial 2 plus x to the power of 4 over factorial 4, and of course it carries on that way. And we're done. Okay, what about integration? Well, in the same way that we're able to obtain the Maclaurin series for a function's derivative simply by differentiating the Maclaurin series of the function, we can obtain the Maclaurin series of a function's integral by integrating that function's Maclaurin series. And that can turn out to be very useful. Indeed, here's a slightly more elaborate example than the one we just used for differentiation. Let's say we're after the Maclaurin series of arctan or inverse tan of x. Well, to find it, we can use the fact that we know the derivative of arctan of x. Indeed, the derivative of arctan of x with respect to x is equal to 1 over 1 plus x squared. And in one of our previous videos, we saw in detail how to find the Maclaurin series of this function. Indeed, the Maclaurin series for 1 over 1 plus x squared is equal to the infinite sum 1 minus x squared plus x to the power of 4, and so on and so forth. And so since 1 over 1 plus x squared is the derivative of arctan of x, or inverse tan of x, we can find the Maclaurin series for inverse tan of x by integrating that Maclaurin series. So that would be the integral of 1 minus x squared plus x to the power of 4, and so on and so forth. Okay, so integrating each of the terms we see here and hypothetically carrying on forever that way, we quickly obtain that the Maclaurin series for inverse tan of x is equal to x minus 1/3 of x cubed plus 1/5 of x to the power of 5, and so on and so forth, plus some constant of integration c. Careful, we mustn't forget the constant of integration here. And to find this constant of integration, we need to use the value of arctan of x when x equals to 0. Indeed, replacing every single x by 0, we quickly realize that inverse tan of 0 will equal to c. And let me insist, regardless of which Maclaurin series we're integrating, to find the constant of integration, we'll always be looking at the value of the function when x equals to 0. Simply because it will allow us to get rid of all of the x terms in the series in order to just be left with c on the right-hand side here. That being said, I carry on. If you're well aware of the value of inverse tan of 0, then that's great. But in case you're not, here's a quick mapping diagram I like to draw to remind myself of its value. So here it is. I have my input box and my output box, and I know that the tan function maps 0 onto 0, and consequently inverse tan has to map that output back onto that input. In other words, inverse tan of 0 has to equal to 0. And so here we can quickly state that inverse tan of 0 is equal to 0, and so the constant of integration c is equal to 0. And I'll quickly box that. There we go. And let me quickly say that the constant of integration won't always be 0. And if you need a quick example to convince yourself of that fact, go ahead and integrate the Maclaurin series for a sine of x that you see here, and use the fact that the integral of sine of x is equal to negative cosine of x. In which case you'll find that the constant of integration will equal to negative 1. That being said, let's get back to the Maclaurin series of arctan of x. Since the constant of integration is equal to 0, we can now state that the Maclaurin series for inverse tan of x, or arctan of x, is equal to x minus 1/3 of x cubed plus 1/5 of x to the power of 5, and we could carry on forever that way. And we're done! We've now seen that we can differentiate and integrate Maclaurin series in order to obtain the Maclaurin series that we're after. And that's it for this tutorial.